And then here we've got parse data safe, and you can see that there's no GS cookie here. And then here we've got parse data unsafe, where you can see that the GS cookie is still emitted. So to summarize what goes on, when you have a function, what happens is there's a whole bunch of variables that are identified as potential hazards that might get overflowed, and they get marked as kind of ticking bombs. And then the GS optimization runs, and it goes and says, well, actually, all of these ones are safe. And then the compiler will look down, and if there's any remaining hazards, then a GS cookie will get emitted, and the function GS protected. So in the ANI case, the ANI struct would have remained potentially vulnerable, and would have GS protected that function. So impact on cookie count, we make savings of a couple of percent with GS opt enabled, so that's good. With the Visual Studio 2010 default GS, we therefore don't have the penalty of all the functions we would have protected with strict GS, but we still would protect all the cases that we were trying to handle. Of course, there are some cases that we wouldn't handle. I mean, I mentioned that we don't handle 8-byte structs, for example. So if you write code where you can overflow a large integer on the stack, then GS isn't going to help you. We've even seen code where a pointer gets overflowed. So if people pass in the address of a pointer instead of the pointer, neither of these cases would get mitigated by GS. And of course, there's things like underflows where the direction of the override goes the other way that GS isn't designed to handle. So GS isn't a complete failsafe. You should still aim to write secure code. We should still have things like pen testing, fuzzing, lots of static analysis tools to actually try and expose the bugs. Really, mitigations are just a last resort. So this is just an aside. Amidst all the performance testing that we did, we came across some odd results. So this was an example. We worked with a student in a local university in the UK, and he did some comparisons between normal GS and strict GS. And you can see that for AES in blockchain mode, for encrypting 16 bytes of data, strict GS, which is the red line, is actually faster than normal GS. So that was kind of puzzling to us, because that's saying you're adding extra instructions, and yet the code is running faster. And that's kind of an open problem. We've got some ideas on why that might happen. But that's kind of an interesting thing, and if you want to look into it, I'd be happy to exchange some there with you. And briefly, I think what's going on there is when you GS protect a function, that has a whole bunch of knock-on effects. So if you GS protect a function, it might be slightly bigger, and so then the inliner in the compiler might make slightly different decisions as to whether to inline that function. Then whether you inline that function is going to have knock-on effects on whether to inline other functions. So you can kind of have this overall, you've got a small perturbation over here that can kind of propagate and have quite a large effect at the end. So most of the time, positive effects and negative effects are going to cancel out. But in examples like that, we think that what we're observing is a case where we just happen, because of the GS protection, to have got a better decision by some other heuristic in the compiler. So to summarize, in Visual Studio 2010, the same /GS switch, we've got a better heuristic that will protect more stuff, and we've got an optimization that will eliminate unnecessary cookies, where the compiler determines it can do so. So yeah, in conclusion, modern exploitation is difficult. I don't think anyone would argue with that. It's not universal in that you are sometimes constrained, but it is still possible. So mitigations are hurdles, they're not preventing it. Exploitation on Windows 7 is harder than it was on XPSP2. Exploitation on Windows 7 isn't impossible. We carry on looking at all the cases that come in. We try and work out where the gaps are. You can be sure we're working on more mitigations for future operating systems and product releases. And we also, of course, a significant part of the work of our team is on automating identification of bugs, so we actually fix the bugs and don't rely on fail-safes. Okay. thank you very much for listening. I'll let Paul head to the bar, and I'll have to take any questions either here or later on this evening, wherever we might end up. Header information is bad. So that wasn't too hard. And actually, we did, in all the tests that we ran, we didn't come across many instances where that happened. It did lead us to catching a couple of bugs in the Windows 7 and release cycle. For things like GS, where it's kind of heuristic and how much you protect is not completely clear-cut, then people scrutinize performance much more closely. And so there, basically what we need to do is work with product teams and try and assess the impact. So, for example, with Enhanced GS, before it got released, before it got checked into the Visual Studio 2010 release, we had built all of Windows with Enhanced GS turned on. We had built all of SQL with Enhanced GS turned on. We had passed all the Windows performance tests, standard performance tests, and the main SQL benchmarks that they were interested in. After checking in, we also verified Office. The compiler team have their own benchmarks of code, like small things like Eon and POVRE, and there's a number of standard computer science benchmarks that they run. So a large part of it is just going through all the benchmarks and then tuning the heuristic to make sure that you pass all the tests. So what I mentioned about us not protecting large integers, that was down to, there was one specific test where we pinpointed that was the reason we were failing, was because that code had a lot of large integers in it, and in particular one of the performance critical functions that we were now protecting had a large integer. And I think that one thing about cookie counts is because it's easy to measure how many functions have cookies, that's what people look at. But actually, you could protect every single function in a binary. If there's only one function that's performance critical and you're not protecting that one, then you'll be fine. So we do run all the performance tests. We do tune as a result of that. The GS optimization, we decided to do that because we thought it would help, and it did help in passing some of those benchmarks. So that's kind of the approach.